All right. Thank you guys for coming today. So as I was as I was preparing for this talk earlier in the week, I was doing a lot of thinking about public speaking in general. Truthfully, I was complaining to my wife about public speaking. You know how men are. We kind of like to think about problems a lot, and they kind of just get shit done. I was telling her, I think speaking in front of an audience is a lot like trying to talk to the hot girl at the bar. So, you know, there's kind of a lot of awkward silences. You're like, hey, my name's Keith. I'm just really into math, and I love computers. So, you know, you have those awkward silences. The conversation's pretty much one-sided. She'll throw you a pity laugh every now and then, but for the most part, she's kind of just checking her watch. You know, how much longer do I have to pretend to be interested? At this point, my wife interrupts me, and she says, seriously, don't you ever do any real work? So I never lied to her before, so at this point I was like, you know, now's a good time. So I said, of course I do. So as the actual speech is, as Josh introduced me, but as Eric said, my name is Keith LaForce. I've been a software developer now for about 8 years. I have 1 degree in computer science and 1 degree in business. Typically, I like to try to apply the lessons learned in both disciplines when I'm trying to solve problems. So today I'm going to talk to you about one problem in particular that I think is applicable to both hackers and the business-oriented alike, and that is data forecasting. So, you know, what is data forecasting? All right, so anybody in the audience, first thing you think of when you think of forecasting, there's no wrong answer here. No, that's definitely wrong. All right, the correct answer is magic. So I know when I first started working with forecasting, I assumed I would need some kind of advanced statistical models or a complex infrastructure of software like SAP, where we've got all these advanced configuration screens. The truth is, to do accurate forecasting, all you need are basic arithmetic skills and Excel. All right, so to reach a ubiquitous language, let's kind of talk about some definitions. So what is forecasting to begin with? Forecasting is simply the attempt to predict a future event. So on the flip side of that, what is forecasting not? Forecasting is not a science. It's not going to be guaranteed. Your forecasts are always going to be wrong. I repeat, your forecasts, they're always going to be wrong. They're never going to be on. You're going to miss every time. So if you have stakeholders that are interested in forecasting and they don't understand that it's simply a tool of estimation, you're probably better off not trying to utilize it. Because essentially what's going to happen is, it's a lot like our estimates as developers, where we give an estimate, the client comes in and says, well, you said it was going to cost $1,000. And I said, well, that was really an estimate in case, you know, my thing that said estimate wasn't clear. You know, they're going to hold it against you. So the same thing happens with forecasting. So you need to be prepared for that. All right, so say my boss, we're just going to give him a generic, just lame name like James. He comes to me with a client, and the client is currently hosting their cloud product on Heroku. Now, one of the problems the client is having is they're exceeding their daily hosting budget because they're not quite sure how many resources they need. So when the client built their system, they had planned for these resource utilizations, but they weren't sure. You know, it turns out the data used on an hourly level varies greatly from hour to hour. Now, the way they've solved the problem is they just run the maximum number of dynos they need to run so their site doesn't crash. Now, obviously, this is very ineffective because you're utilizing resources that you don't technically need. So how do we solve this problem? So today we're going to talk about a forecasting system and hopefully find a way to alleviate that problem. So the forecasting system that I've developed, I've just codenamed it Silas. It's hopefully going to help us address this issue that, you know, this particular client may have, or in the case of other problems, like this is talking about web traffic, but forecasting can really be applied to any set of data. So this forecasting system, Silas, I created, we're going to go through 5 techniques on the first half, and then the second half we're going to kind of talk about the architecture of Silas and how I kind of set it up for you know, people to actually use. All right, so we're going to start incrementally. We're going to start with the easiest forecasting technique, and then we're going to kind of move from there. Okay, that's not really the first one. All right, so obviously this is not very easy, so this is the last forecasting technique we're going to work with. But by the end of this talk, you guys will understand how this works and when you would want to use it. So the first technique we're really going to start with is called the naive method. So the naive method simply states that when you're forecasting for a period, you use the value from the previous period. So in this case of this data table we're looking at, the forecast for period 2 is 10, which simply comes from period 1. So, anybody who thinks they can tell me what the forecast for period 5 is? 42. Oh my gosh, you guys are geniuses. All right, so we kind of knew that would be easy. So now that we've covered the naive method in under a minute, let's talk about the pros and cons. So the pros of the naive method are that it's very simple to use, it's very easy to understand. I mean, you can pretty much grab anybody off the street and have them do this. So when would you want to use it? If your career has just reached like rock bottom and you have no more dreams of success, then you should use the naive method. All right, so this slide right here, this represents the front-end dashboard of Silas. So this is going to kind of show how our forecast model does over time. So if I can get my mouse right here, we're going to start this. All right, so this is showing a few different things. First off, we want to define like what our units are and what our period is. So this is working in number of hits per hour. So in our business case, the client is requesting a forecast per hour, so we're looking at how many hits they get per hour. So this is showing how well the naive method is doing. So if we take a look at this, we can kind of see the white line is the true data. So that's actually what the client is recording to us, what the data values are. The red line is what the forecast is going to be, like what we're telling it, what we assume the forecast will be. So as you can see, since it's the naive method, it's basically just shifted over one period. So that's kind of how those graphs are set up. So we got a couple other tiles over here. We got this data table tile. So this is actually showing, the data as it's coming in if you needed to see that. So we've got the period number, the actual value, and then the forecasted value. In addition to that, we have what we call the mean average error. The mean average error is simply our measurement for success. So first off, to talk about mean average error, let's talk about what error is. So if we're looking at our previous data table, error is simply the difference between the true value and the forecasted value. So in the case of period 2, the error is 25 minus 10 or 15. So that's what our error is going to be. So mean average error simply averages those errors over the life of the model. Now, it may seem odd at first, but the numbers you're actually seeing here are not future predictions. These are the historical data, and we're actually forecasting what we would have been in the history of the model. So why do we do that? Why can't we just say, just give me the next value? Well, in order to validate your models, you actually have to run it against a historical data set because you can't predict the future, so you don't know how well it's going to do. So you validate your model against a historical data set, and that tells you how well you're actually doing. All right, so when working with these simple methods, how far in advance do you think you can predict? One period, great. All right, so why can you only predict one period? That doesn't seem very useful. When you're working with data, these simple methods, one period is typically good enough for most business cases. So in the case of our business client, we're working with Heroku. We're just trying to determine how many dynos we need to spin up in the next hour. That's plenty of time for us to do that. Now, if you look at the magnitude of the period, it may vary. So if we're looking at sales forecasts, this may be yearly or monthly. 1 year ahead is actually pretty good if you're looking at sales forecasts. So it kind of just depends on what data set you're working with. Now, there are needs for being able to predict further into the future, and we're going to show an example of that. For example, on our last technique, we're actually going to be able to predict 12 hours into the future rather than just 1 hour. All right, so this is our second method of forecasting. This is called moving average. Moving average is simply one simple step away from the naive method. If we're looking at this equation, we have a couple different things going on. One is the A variable. This represents our actual data. So A, t minus 1, is our previous actual value from one period ago. So if we're looking for a forecast for the current period, we're simply taking an average of n number of previous periods. So if we were working with 3, an n value of 3, we'd average the past 3 values of your data set. So let's kind of see how that compares to the naive method. So we still have the same things going on. We've got an error rate, we've got an MAE. I don't know if you guys noticed, the MAE and the naive is around 100 and something. I don't quite remember. In this case, it's actually a lot higher. The reason that is we have large fluctuations in our data change. Excuse me. So if you're looking at the white line, you'll see that there's large differences where it moves from one low period to one high period. It's hard for a moving average to keep up with that in certain cases. So in this case, our n value is 3, so we're only looking at the past 3 periods. So actually what happens is it takes about 3 periods for it to realize that the data direction has changed and start moving in that direction. So that's where kind of our forecast error comes from. It takes it 3 periods to catch up, so our error values are a lot higher. Now in this tile, we actually have an error percentage. So this error percentage just represents over the life of the model how far off we are. Now 2% is not that high. This data set is actually relatively close to each other. So most of the forecasts end up being pretty close, so the percentages are relatively low. Now if we were working with something more complex, that might be higher, or if we were working with a really intense data set like something in the medical field or something in the Department of Defense, 2% could make or break you kind of thing. So it just depends on what kind of data you're working with. All right, so we're going to move on to the third one. This one's called simple exponential smoothing. It works similar to the moving average in that it interpolates data over time. There is one key difference in this one. A, it looks a lot simpler, and B, we're actually using the previous forecast, whereas in our previous 2 algorithms we were only looking at the actual values. So why do we do this? Interpolating the data over the previous forecasted values just allows for a smoother transition, which is why this is called exponential smoothing. So we have a new concept here. It's the alpha character. The alpha character represents our smoothing constant. So this is like how smooth do you want the data to be changed. So in the moving average, we had an n value of 3. If we had an n value of 100, if you can envision the data, it would take 100 periods for the data to get rid of old data. So it doesn't move very well with new changes to data. So if you had a very slowly increasing line of data, that would be great because it's kind of moving in the right general direction. In our case, the data is moving like this. So it changes every few periods, so moving average can't keep up very well. The same concept happens in exponential smoothing, where the alpha value kind of determines how well it transitions. The higher the alpha, the more responsive it is to data changes. The lower the alpha, the less responsive it is. So let's see how well this one performs. So we're going to let this kind of catch up a little bit. So as we see the forecast moving, we see something interesting. The forecasted values are pretty much staying the same. Now the reason this is occurring is my alpha value for this model is extremely low. It's like 0.02. So that means the data can only change at a rate of basically 2% kind of thing. So since the data is moving so rapidly and it's depending on so much history, it pretty much just stays in the same line. So it's not great for this model. So the error on this is relatively high. Now one way we can improve this is just by increasing our alpha value. So if we increased our alpha value closer to 1, we'd actually see it start following that curve a little bit better. I just wanted to give an example of what it would look like if you were doing it incorrectly. So how do you choose that alpha value, though? That's the question. Because that's pretty much the only variable that's in that equation, so you have to define that. So how do you define it? All right, I lost my mouse here. Sorry, I don't have this mirrored, so I'm trying to find my mouse. There we go. All right, so let's look at an example of this. So we're actually going to switch over to Excel here and kind of take a look at how you would do this by hand. So the Silas system does this for you, but if you're just Joe Blow off the street, how would you just do it off, if your boss came to you and said, what do you think this is going to be a month from now or an hour from now? Hopefully he's not coming to you every hour asking you what it's going to be. All right, so if we're looking at this Excel sheet, sorry, I'm having a really hard time seeing my mouse here. All right, so we have a few things going on here. On the far left-hand side, we have our period. So in this case, we're doing sales forecasts, so this is a weekly sales forecast. So we have sales. This is our true data. So these are the actual numbers. Remember, we always validate our models against historical data, not against something we don't know that's going to happen. So in the first period, there's nothing to forecast because there's no previous value. So we simply set that to NA and don't worry about it. For the second value, we don't really need we still can't use an equation here because we don't have a previous forecast value. So we don't actually start forecasting until the third period. So I already have this equation set up. It's simply the equation that we looked at before. We take into consideration the alpha value, the previous forecast, and the previous data. So then we have our error rate, and this is actually going to tell us what our error for this model is. Alright, so what we need to do, we have the sales data, so we need to predict, see how well our error is doing for the whole model. So let's just copy that equation. We're just going to copy it all the way down. Alright, so now we've got all of our errors, so now we need to calculate our mean average error. So over here, let's get an average going. It's telling me there's an error in my formula. I figured out the mouse now. Okay, yes. Alright, so now we're up here. So we have our mean average error. So if we change this alpha value, let's just increase it. We see our error actually went up. So you're like, well, okay, I guess I'll go down. It was originally 0.6. Well, this is slow. Okay, that went down a little bit. Let's go again. Okay, nobody wants to do this, right? So how do you pick your alpha value? So let's use a tool that Excel has called the solver. So we're going to look at solver, and let me bring it over here. Now the way solver works, you pretty much just set a goal that you want and then tell it what variable you want to change, and it just solves it for you. So what we want to do is we want to minimize our error. So we're going to set that. We want to change the alpha variable. And then finally you can set some constraints. These are already set up because I did this earlier. Basically your alpha can only be between 0 and 1. I set the constraints a little bit more restrictive. That's anything between 0.1 and 0.9. There's no particular reason for that. They're just numbers I chose. Alright, so we hit solve. And it's going to run through the various permutations, and eventually it's going to find an alpha value that minimizes our error. So in this case, the perfect alpha value for this data set is 0.59. So if you were doing this, you would pretty much run that and then you would be done. Now at this point you can start predicting one period ahead. So then you could run one future prediction and that would be it.
Yeah. So you mentioned it's for this particular data set. So as as you begin forecasting, let's say you're forecasting for a year, should that alpha value change over time as well as the data changes?
It could. I didn't want to get too deep into this, but normally what you actually do is you actually set aside a subset of your data, and that's called holdout data. So you actually validate your model against non-holdout data, and then you see how well it performs on the holdout data, and that tells you you're actually doing well. That is a true validation, because if you do it on the whole data set, it's actually optimizing your alpha value based on your whole data set, which is taking every variable into consideration. You really want something that we're going to live forever. So typically your alpha value wouldn't change from year to year or period to period if you did it that way. I didn't want to get too deep into that. Alright, so let's switch back. Alright, so the fourth technique we're going to look at is double exponential smoothing. Extremely similar to simple exponential smoothing. We're adding an additional equation. This is going to measure our trend. So now we have to define what trend is. So if we're looking at a normal data set, so far we've just been worrying about randomness in data. So like the values change from period to period. Now in data you can have overarching kind of similarities. So in this case, this is called an upward trend. So the data is actually moving in a general direction upward. The previous three techniques will actually work for this. However, it takes longer for it to catch up. So the double exponential smoothing kind of just gives us a leg up and starts helping us get to our forecast more quickly. All right, so looking back at the equation, we have a new constant here called beta. Beta is just the constant. It works exactly the same as alpha. It's just used for trend data. So we have two equations now, and to get your final forecast, you just add the two values together. All right, so let's see how double exponential smoothing holds up against our data set. All right, so there's a couple things to note here. One, the error started out pretty low, but as over time, it's going to kind of even out to around, whatever it is right now. So if we're looking at it, there's a few things to notice. One is the forecasted values actually they are following the trend, but this is not a global trend. This is kind of what is called a local trend. So it actually follows the data up, and then it realizes, oh, I really have to go back the other way. So it actually overcompensates because it takes time for the model to kind of catch up to the data. So this isn't really ideal either. So how do we handle these kind of local ups and downs? Like if I let this run further, you'd see that the data actually starts moving upward. So how do you kind of handle that? All right, so the final one we're going to go over is called triple exponential smoothing. And yeah, you guessed it. We're going to add a third variable, and we're going to add a third equation. So this one's a little bit more complicated. This is the one we were looking at from the beginning. The equations are pretty much the same for the forecast and the trend. We're now adding a new component called seasonality. So seasonality in data is exactly what it sounds like. If you're working in retail sales, your normal seasons are going to be high at Christmas, low the rest of the year. So there's always a spot in your data that's going to kind of come up and then come back down. So those are those local ups and downs we were looking at. So looking at this, the equations are pretty much the same. We're in the third equation. There's a little bit more detail. You actually have to do something called calculating the seasonality index. I didn't really want to get into that because it's kind of mundane. If this looking at equations isn't mundane enough. So I don't want to get too deep into that, but it works very similar. If you want more details, feel free to ask me afterwards. I'll be glad to shoot you an example or something. So let's kind of see how this one performs on our data. Now we're going to let this one kind of build up a little to get some momentum. Kind of needs that initial data to kind of hone in on the true data. But what we're going to see is the red line actually starts getting closer to the true data over time. And eventually it gets to the point where it's starting to follow it almost directly. So like on this downward slope, you can see it's pretty much dead on as it gets to that point. And you notice the error rate is extremely low. In this particular case, we're talking about over 33,000 hits were like 65 off. So, I mean, that's relatively good. So the triple exponential smoothing gives us an added benefit of, previously we were talking about you can only predict one period ahead. If you're using triple exponential smoothing, you can actually predict an entire season ahead. So in this particular case, we defined a season as 12 periods or 12 hours. We could just as easily made it 24, and then we'd be able to see a day into the future. So it kind of depends on how your data works and what the details of that data are. All right, so now that we've covered the 5 techniques, we're kind of going to talk about into Silas and how it's kind of set up and what the architecture looks like and where it can be improved. So looking at this graphic, as you can see, like most applications, Silas has 2 components. It has a server side and a client side. So the server side has 2 endpoints that it's currently looking at that you interact with it. So the first one is called server endpoint. Server endpoint is simply a REST API. It's built using Microsoft's WebAPI technology. All it does right now is feed data. So you feed data into it, reads it into the system, and then it starts using it. The second endpoint is the Silas hubs. This is built using Microsoft's new real-time framework called SignalR. It allows you to actually push data to clients rather than requiring them to come to you to actually get the data. So this is what's driving that graph. So we're actually pushing data down to the client, and then that client's reading that data in and then doing something with it. So if you had a production system where your inventory management depended on these forecasts, you just push it into your inventory management system, and from there it can do whatever it needs to do with it, like make orders, do those kind of things. So the other pieces to the server side, where the data comes in, we store it in the database just through a data repository. That's a typical pattern for this. And finally, the forecast library is the main component of Silas. So if you wanted to use this, you could technically just download the forecasting class library and just start using that. There's no need you don't need all these other pieces to make it work. So the forecasting library is set up using a strategy pattern. I'm going to get into that in the code in just a little bit. We're not going to do too much of the code because Jay Miller's not interested in that. All right, so the final piece of this is the client side. So the client side has two pieces, the data feeder and the hub piece, which is just the client side version that's reading that data in. So the data feeder is simply for this demonstration, essentially just reads an CSV file, pumps data in through the REST API. The final piece is the hub piece. So this uses a couple different things. So the dashboard is set up using something called dashing. It's actually a Ruby concept. I just basically ported it over and just stole all their CSS. And then the other piece of this is the graph is built using D3's JavaScript library, so that's how that graph's actually built. So the data comes in from the data feeder, talks to the forecasting library, gets a forecast, pushes it down to the client, and then gets that value and displays it on the graph. All right, so we're going to switch over and kind of look at the code here just for a minute. So let me get my Visual Studio over here. And if I didn't mention this before, this is all written in .NET and JavaScript. So as discussed, we had a few different projects or applications here. So we have the server. This is actually setting up that REST API. This uses a self-hosted server, and it just sets up a simple REST endpoint for you to read data in. The data feeder is what actually sends data to that server, and then the forecasting library is made up of the forecast class and the testing framework. All the actual code is driven from the web project, and that's where we kind of set up this presentation and read data into the dashboard. So looking at the forecast, there's a couple things to note. One is the strategies. So for those who don't know, the strategy pattern is simply a way to kind of create a common interface for an algorithm. So in this case, our algorithms are, forecasting models. You don't care what the details of a forecasting model are. You just want to say, here, give me a value back of what the forecast is. So this kind of sets that up. So we have strategies for each of the ones we talked about. So if you look at the naive method, you'll see that all it's basically doing is looking at the data. It does some error checks here, and finally it just says, give me the value for the period of the previous period. Now what's nice about the strategy pattern is if we want to add new models, we simply add a new strategy, and then anybody can leverage it. So once that new strategy is in there, the interface works the same, so anybody who's trying to interact with it just has to worry about, I don't care what you do under the hood, just give me the next value. So now let's see if I can minimize this. All right. So what is the roadmap for Silas? So we have a couple of problems with it right now. The first problem being there's not a great public API for it. Essentially all you can do at this point is read data into it. That's all you can do. The Silas piece works great if you want to push data down, but that's not necessarily the paradigm that everyone wants to work with. So what I'd like to do is set up a more friendly public API where you can retrieve your forecasted values. The second thing is it needs to be easier to modify those parameter values, alpha, beta, gamma. As it exists today, they're actually hard-coded into the model, or hard-coded into the SignalR stuff. It's not great if you want to make changes to it. There's no way. You just have to change the code, redeploy, see what happens. So what I'd like to do is add to the dashboard the ability to change those parameters on the fly. Once we get that set up, then we can kind of start moving in the direction that I was originally intending, which is to make it extremely intelligent. So one of the problems with forecasting is trying to determine what these values you want to use are. How do you know if your data has a trend upward? Like, you don't want to bring it into Excel, look to see if it has a trend upward by graphing it, and then go modify your alpha value and then kind of change it back and forth. So Silas should be able to intelligently determine if there's a trend upward, and if there is, it can also determine whether it's seasonality, and then it can actually determine on the fly what your forecast model you should use. Like, you shouldn't have to say, I want to use triple exponential smoothing. You should just say, here's my data set, give me the next value. So from there, it needs to be able to automatically choose the alpha value, so that would just involve implementing some kind of solver technique similar to the way Excel works. And finally, we need to flesh out the confidence intervals. So on that dashboard, there were two tiles. They were labeled CI high and CI low. They actually weren't doing anything. They were just giving you what the forecast value was. A confidence interval simply is a range of values. So as we mentioned before, your forecasts they're always going to be wrong. So how do you kind of guard yourself against that. You set up what's called a confidence interval where it just gives you a range, and then you say, okay, I'm 95% confident it's going to be between 10 and 20 or 10 and 15, and that gives you kind of a leg up to say, well, we'll plan for the worst but hope for the best. All right, so we've gone over a lot today. We've gone over Silas and how the architecture works. We've gone over 5 different techniques: naive, moving average, all the exponential smoothings, and what the differences were. So just to sum up, don't use the naive method. Moving average can perform relatively well if your data doesn't change much. Simple exponential smoothing should kind of be the default. That's where you want to start. And finally, if you have a trend, use double. If you have seasonality, use triple. All right, so here's my information. We currently have Silas sitting out on GitHub. It's completely open source. I mean, if you guys want to start hacking on it, you're welcome to. But for now, it's pretty much just me. It's dependent on Microsoft.NET, SignalR, and just kudos to the Dashing guys for setting up an extremely nice interface. I wish they had a .NET port because it really sucked trying to steal all that. All right, so do we have any questions?
Eric, are there any cons to the triple exponential smoothing? Like, obviously in this example, it looked like it was the best.
It looked like it was the best, and the reason it was the best is because there was a seasonality component. If there is not a seasonality component, it's not going to perform very well. Because essentially what it's doing is it's trying to predict something that doesn't exist. So if you had something that was just a general trend upward, like, it would probably lag behind. Chuck, you look like you have a question. You're just smiling.
Did you have to get up with Heroku to solve their auto scaling problem?
I did not get up with them. I've looked at. They did not. They do have. I've seen a couple of tools like that where it'll actually auto scale for you. I'm not actually too familiar with them, so I don't know how well they work. This was kind of just a great example of when you would need it. Honestly, they probably, with resources utilization like that, like, those probably work good enough, kind of thing. Like, you don't have to be that accurate on the number, because, you know, a dyno can hold, let's just say, 1,000 users. Like, you don't have to be that accurate on how well you do.
What parallels do you see to do artificial intelligence research and portability?
It's very similar. The main issue, or the main difference here, is we're not actually doing any statistics. Like, it's all arithmetic. Like, you know, you could teach 5th graders to do this if you just give them the equations. I mean, they're basically adding and subtracting. So artificial intelligence is a little bit different in that it does get more into statistics, and they start getting more complicated algorithms, like, you know, trying to leverage neural networks or, you know, something along those lines. You could use this for certain small pieces of it, but overarching algorithms probably wouldn't hold up to it.
Would you use like a bell, like when you choose your holdout data, would you use like a bell curve to figure out?
That's a great question. When you're using your holdout data, typically my rule of thumb is to use about 80% real data, 20%. But I mean, you can get more intelligent about it. It usually works well enough. Like, if your error rate is relatively low, you get to a point where you say that's good enough. Now, like I said, if you're in inventory management for BMW and you need to know exactly how many, you know, gear shafts you need, you know, you want to be a lot more accurate with that. All right. Well, thank you guys for coming, and thanks for coming out to see Skookum.